Hi everyone. In this video, what we're going to do is we're going to analyze this function f that's shown here. We're going to find the critical points. We are going to find the intervals for which the function is increasing or decreasing. And we're going to find the inflection points and the intervals where the function is concave up or concave down. Finally, we will plot points and sketch the graph. And we'll also find the limit of this function as x goes to infinity and x goes to negative infinity. For the critical points, we take the derivative and we use the power rule. We have 3 times the derivative of x to the 5th, which is 5x to the 4th, minus 20 times the derivative of x cubed, which is 3x squared. And what I want to do is I want to factor this. Why? Because I'm going to set f prime of x equal to 0 and solve for x. So part of that is I'm going to factor. So pretty clearly I can factor out 3. But I can also factor out from 5 and 20 the number 5. Put a dot for multiplying. And then also I can factor out from x to the 4th and x squared, which leaves behind on the first term, what? 3 and 5 have been factored out, and we factor out x squared from x to the 4th. So we get x squared right here. And then for the second one, I factored out the 3, and from the 20, I factor out 5. So that leaves 4 behind. And we also factored out x squared. And then this becomes 15x squared, and then x squared minus 4 becomes x minus 2, x plus 2 in my factorization. So that's the derivative factored. And then what I'm going to do over here on the right is I'm going to solve f prime of x equals to 0. And so that gives 15x squared, x minus 2, x plus 2 equals 0. So x equals 0, x equals 2, x equals minus 2. So those are our critical numbers. All right, now what I'm going to do is I'm going to make a chart to determine where the function f is increasing and where it's decreasing. And that will tell me whether these critical numbers correspond to local maximum or local minimum or neither. So let's go ahead and make a chart. And my chart is what they used to call a sine graph. I think maybe people still do. It's a sine chart. It's a chart that's going to show us where the derivative f prime is positive or negative. And what we do is, in fact, is we just, we make a number line. And what we're going to do then is we're going to break the interval, or the x-axis, into intervals, and those intervals are broken up with endpoints, which are the critical numbers. And then what we'll do is we'll determine whether the function is positive or negative on those intervals, or actually the function f prime. We're going to determine whether f prime is positive or negative on those intervals. And so what I do is I plot points, and so I'll go ahead and do that. So here's x. But where am I plotting the points? I'm plotting the points into f prime. So let me go ahead and write down what f prime is, and then as we go, maybe this will be clear why I'm doing this. So I decided I'm going to write down the factored form of f prime of x. But maybe someone wouldn't do it that way, but that's the way I'm going to do it. And what I'm going to do then is I'm going to pick one number, a convenient number from each of these intervals. And so what's going on is that the real line is being broken up into 4 different intervals, and we're going to look to see whether f prime is positive or negative on those 4 different intervals. And so I just have to take what they call a test point from each interval, and you pick a convenient one, like -3. So if I put in -3, I'm going to get some value. But what I'm really interested, though, is not at all what the number ends up being. What I'm interested in is whether that number at f prime is positive or negative. And see, what I have is I have a negative times a negative makes a positive. So at negative 3, f prime is positive, but that means that f prime is positive on the entire interval. And the reason is that f prime only changes from positive to negative at places where f prime is equal to 0, at critical numbers. Critical numbers are also where f prime is undefined, but this is f prime is a polynomial, so it's defined for all values of x. All right, so then I'll pick another number going to the next interval. I'll pick negative 1. And so at negative 1, I get 15 times negative 1 squared, negative 1 minus 2, negative 1 plus 2. And I'll have 15 times 1 times negative 3 times 1. And you can see that I have a positive, negative, positive. So that makes a negative. And so why am I doing this? Because I'm looking at f. And so what I see is that f prime is positive, f is increasing. That's why I care about this. And when f prime is negative, f is decreasing. And the result is, my conclusion is that by looking at the way f is behaving with increasing and decreasing, it's increasing and then decreasing, and it changes from increasing to decreasing at negative 2. That makes this guy negative 2 a local max. A lot of times I just write max instead of local max, but so that's what we have there. Now I'll pick another point, test point in this next interval. I'll put in 1, and I have 15, 1 squared, 1 minus 2, 1 plus 2, and that's going to give 15 times 1 times negative 1 times 3, which is negative. It's not really that good to write equals negative. It's a little bit bad notation. So I have negative here, and then the graph is increasing again. And so this means that x equals 0 is a critical number, but it's neither a max nor min. And then I'll pick one more point, 3. And so I'll have 15, 3 squared, 3 minus 2, 3 plus 2. Why am I picking 3? 3 is just any number that's on this last interval on the right. And by the way, there's a few shortcuts, or if you really want to just study more on how to make this go a little faster, but I think we're not going to do that right now. It's especially with polynomials. I mean, there's a reason there's a pattern of positive, negative, negative, positive, and the short answer is that our function does not, f prime does not change from positive to negative where x squared equals 0. See, here's x squared equals 0, of course, it's 0. X squared is always positive, so x squared doesn't change sign, but the f prime does change at when x minus 2 is 0, which is 2, and x plus 2 is 0, which is negative 2. It does change. Okay, it has to do with the power being x squared. All right, so anyway, we did that, and let's go over here and say that this is a local min. Okay, so actually we've already can sort of start sketching the graph. The graph is going to go up, down, and by the way, so over here you have f prime is 0, so it levels off for an instant. And then it goes down, levels off for an instant because we have another critical point, then it goes down again, and then it goes back up. So we have these 3 critical points. So we had the 3 critical points, which I suppose I could highlight, of negative 2, 0, and 2. And so what we're seeing is that the graph goes up and then down because I see positive, negative, and then it goes down and down again, but there's an instant where the tangent line's horizontal, and then it comes back up. So we already have that a lot of here, shown here. Now the inflection points are where the function changes from concave up to concave down. Let's find the inflection points to f. In order to do that, I need to start off with the derivative, f prime, because I need to find the second derivative to find the inflection points. So what we do for the inflection points is we find the second derivative, set it equals 0, and solve. So I have f double prime of x. This is 3 times 5 times the derivative of x to the 4th, which is 4x cubed, minus 20 times 3, the derivative of x squared is 2x. So, factoring again, we can factor out a 3. Well, actually, see, you can factor out 4 times 5, because here's 4 times 5 is 20. So 5 times 4. And we can also factor out x. So old factoring, okay, that leaves behind x squared. And let's see, we took out 20 and we took out 3 and leaves 2 behind. So if I set f double prime of x equal to 0, and so this, by the way, is equal to 5 times 4 is 20 times 3 is 60. So 60x, x squared minus 2. So if I set this equal to 0, I have 60x, x squared minus 2 equals 0. That gives x equals 0 or x squared minus 2 equals 0. And then I get to x squared equals 2, which gives x equals not just square root of 2, but plus or minus the square root of 2. So you want to, gotta get that plus or minus there. Gotta remember to do that. And then we make another chart to show where f is increased, or f is concave up or concave down. And the chart looks really similar to our last chart. We start off with a number line, and what I'm going to do is, right here is 0, and then I'm going to put square root of 2, roughly speaking. The square root of 2 is greater than the square root of 1, which is 1. It's less than the square root of 4. Square root of 2 is less than the square root of 4, which is 2. So, like here's negative 1's right here, positive 1's here. And so it's true that it's a little bit of trouble doing this because it's not an integer. But that's the way things work, is that not everything's an integer. Okay, and so now what I'm going to do is I'm going to try to determine whether f double prime is positive or negative. And so I plot points, and I have x. And let's see, I'll write down f double prime of x, and I'll try to, you could do a factored form or not. So, but I'll write the f double prime is 60x, x squared minus 2. And I pick 1 point from each interval. So, okay, maybe I'll just put this a little lower so it's easier to read. Okay, so from our interval, I'll start from the interval on the left here, I'll start off with a test point being negative 2. So I have 60, negative 2 squared minus 2, which makes 60 times negative 2 times, this is 4 minus 2, so it's going to be times 2, and so that's negative. And the point being then, if f double prime is negative, then f is concave down. And then I'll pick another point I'll pick a point from the next interval. So I'll look at negative 1 here. And I'll just go ahead and just go about this. And someone would say, well, this is tedious. And I'd say, well, yeah, that's definitely true. Okay, so 60 times negative 1 times negative 1, and that's positive because I have 2 negatives there. And so this will make f is concave up. Now the thing is, if I write like this, it's not a little misleading, because what happens is that the function is concave up, but it's decreasing. If you remember that during that interval, f will be decreasing. And then if I put in 1 here, right? So between 0 and negative 2, the f is decreasing. So in this interval, f is going to be decreasing, so it's going to have like a half of a smile. Let's put in 1 here for x. It's from our next interval. So that makes negative. And on this interval, still f is decreasing. So when I write concave down, it's, I mean, you can make the whole like arc, but it's not really the whole arc. It's only half of the arc because it's still decreasing on that interval. If you can go back to the chart above here, between 0 and 2, it's still decreasing. And then, I mean, the thing is that from the chart above, we can guess that f is increasing over on this next interval. So anyway, this is concave down because f is negative, up because, because f double prime is negative, up because f double prime is positive, down because f double prime is negative, up because f double prime is positive at 2, on the interval containing 2. You can plot that point really easily. That's going to be 60 times 2. 2 squared is 4 minus 2 is 2, so that's positive. So that gives us this, we have these inflection points, and just gets us closer to figuring out what's going on there. Okay, now we're going to find these limits that go to infinity. So what we do is, these are polynomials. Polynomials behave like their highest degree term. So even though we have this 3x to the 5th minus 20x cubed, when we find the infinite limit, or the limit as x goes to infinity of a polynomial, we just look at the first, not the first term, the highest degree term, which, since I like to write the polynomials where the highest degree term comes first. But the one that has x to the 5th, that 5 is a greater number than 3. So then I look at this guy and I look at x to the 5th. Well, as x goes to infinity, x becomes large, raised to the 5th is still large, multiplied 3 is large, and that's infinity. The thing I'm really looking for is to see if this is positive. Put in a positive number, raised to the 5th power times 3, all positive. Over here we get the same idea. We look at the highest degree term, 3x to the 5th, but even though I wrote it wrong here, it's not as x, I'm looking not at this one as x goes to infinity, this one next x goes to negative infinity. And the key is, x is getting large, and multiply by 3 even bigger. So it's going to be infinity, but not, well, it's infinity, but it's negative infinity, because we're putting in a large negative number, and a negative number to the 5th power is still negative. Multiply by 3, negative. All right, and what does this mean? It means, I think we could have known this anyway, but if you look at this picture here, when we, this guy here, it's this increasing, decreasing. What's going on is this guy's not just sort of, it's going to go, it's going like this. Polynomials are going to go way up or way down, just like y equals x squared or y equals x cubed. So I just want to point that out. That's what this means when I say the limits are infinity and negative infinity. Okay, now we're going to plot the points, which is, not sort of a waste of time a little bit watching me do this. But which points am I going to plot? I'm going to plot critical points and inflection points. So let's start off with -2. That's where the graph above where it says that we have a maximum. So it's probably better for me to go a little bit quickly on this. So this is going to be 3 times -32 minus 20 times -8, which makes 96 plus 160, which makes 64. And then we have an inflection point, as we said, at, where was it? Negative rad 2. So we have 3 negative rad 2 to the 5th minus 20 negative rad 2 to the 3rd. And the thing is, I'm going to avoid using a calculator. I'm going to factor out, the trick is you factor out one of the negative rad 2's. So I have negative rad 2, and that's going to be leave 3 negative rad 2 to the 4th power minus 20 negative rad 2 squared. So this is negative rad 2, 3 times, well, you think of this negative rad 2 to the fourth as negative rad 2 squared and then squared again. Minus 20, negative rad 2 squared is just 2. So this is going to be negative rad 2, 3, 2 squared, negative rad 2 is 2 squared. Negative rad 2 squared is 2. So I'm going to square that. So say this is, okay, so this is 2 squared is 4 times 3 is 12 minus 40. So I feel like I did a lot of work, but now I'm thinking, is this right? And I think, okay, this is what I got, I guess, when I did this before to warm up for this. Okay, so it's 28 rad 2. I mean, a lot of people say, well, why don't you use a calculator? Why am I living in some sort of world where I'm not using a calculator? But anyway, that gives the exact value. I don't think you'll get that from a calculator. The exact value. You get a decimal approximation on the calculator. So anyway, you get 0 for the next one. Sort of bled into this. Put this up here. Maybe highlight these. All right, I want to save a little time and go and just point something out. These are both, we have for f of x, it's x to the fifth, x to the third, and separated by subtraction. That makes it an odd function. That's another whole topic, but f is odd, which means that f of negative x equals negative f of x. And so that makes it a little bit quicker when I when I plot points. So if I put the inflection point square root of 2 in, I'm going to get, say when I put negative rad 2, I got 28 rad 2. If I put the opposite of that rad 2, I'm going to get negative 28 rad 2. So you can check that. And then you have a local min at 2, and the same sort of thing happens. At negative 2, you get 64, and then at positive 2, you get negative 64. And you can work that out, but it is because f of negative x, or f of, maybe you say f of opposite of x equals opposite of f of x. That's because you have an x to the fifth and x to the third, and you can verify it as that property. But now if I sketch the graph, what I want to do, I guess, is not make the x and y axis to scale, because the y values are so, they're sort of big, sort of large. So that's pretty commonly done when you have graphing calculators or software, that they sketch the graph, but they don't make the x and y to scale. Okay, so, but, we'll see. Let's see how it goes. Okay, so I have negative 2, and at negative 2 I have 64. I'm going to make my y-axis go by 10. 10, 20, 30, 40, 50, 60, so 64 is up here. And so the thing is, you have to, so this is a local max. At the same time, why I think it's really quite difficult is that we have this chart that we're going to look at. But it's going up and then down. It's curved though. And we also know from this chart that it's concave down around negative 2. So we have both those charts. It's going like this. But then we have an inflection point, which I'm going to call IP, just to shorten it. Inflection point at negative rad 2, and then we get 28 rad 2. I hate to say I'm not going to bother to try to estimate what that is, but I suppose I could, but it's going to be around 40 or something anyway. But what I'm focusing on is shape. Now, see, the fact is that it's concave down, but then it becomes concave up until it gets to 0. The whole thing might have been better also if I stretch this out. I want a good picture. Let me make it so that it goes like this. Negative 1, negative 2. I want a really good picture. No, just joke. I want it to be decent. Okay, so there's my inflection point, and the local max, as we see, is, as we saw, is negative 2, 64. Okay, so then you get this inflection point, but then it goes concave up. And also at x equals 0, you have an inflection point where it changes from concave up to concave down. See, that's what our graph shows us over here. Between negative rad 2 and 0, it's concave up. And then also we have a critical point, an inflection point, which is also a critical point at the origin. And then, see, it's an inflection point, so now it becomes concave down. And we'll come to, this is a positive rad 2, so it's around over here. So it's going to be concave down until we get to the next inflection point. Let's just say this is not as good at all. Okay, concave down. So that's another inflection point at rad 2, negative 28 rad 2. I feel like everything I was doing was sort of neatly done, but now my handwriting is getting a little messy, and I feel like the labeling is something that probably, if I were doing this like on a test, I would want to do later. So this is 1, this is 2. Okay, I probably want to come back and do that later. All right, then it goes concave up. And also we want the polynomial to just keep going. So this is our local min, which is at 2, negative 64. And now, see, I feel like the way of drawing is maybe what I learned like when I took an art class like 100 years ago or something, when I was a young guy. But I don't think it's that good to have this sort of scratchy look. That would be like for more artistic look, but we want it to look a little more smooth than that. So I'm going to just go with a thicker pen. Oh, okay, well that wasn't so good either, my thicker pen, but anyway. I could go back and try to do a new one. Well, you don't want perfect to be the enemy of good. It's pretty good. It's not perfect, but pretty good. But again, what I want to do is just think about the shape, especially concavity. Concave down, then you come to an inflection point. Concave up, inflection point. Concave down, inflection point. Then concave up. And I want to make sure it keeps going up and up and up to show that limit. It's infinity on one side, negative infinity on the other side. And I definitely want to show those max and min. And notice I'm not that concerned of getting the y coordinates, very precise. I'm more interested in the shape. Even here, I want to make it clear that that's a critical number. I want to make sure that that levels off. But I'm interested in concavity, critical numbers. All right, I guess that's all I'm going to do. But oh, by the way, why don't I just copy or why don't I at least write down what this is f of x, just to make this a finished product. F of x equals 3x to the 5th minus 20x cubed. All righty, and that's our graph. There's a bunch of places where you can look up those. I think I could still keep improving, go back and improve my handwriting here and there. Okay, so that does it. All right, thank you. Bye.